So here in lecture 2.6, we're going to finish our discussion of computational Boolean algebra by completing our discussion of recursive tautology. So at the end of the last lecture, what we showed was a computational vision of how this would work, a recursion where if we cannot answer the question as to whether the function is a tautology, we can pick a variable, use Shannon cofactoring, split things, turn them into simpler pieces, and build the outlines of a recursive implementation. However, there's a whole bunch of more interesting properties of Boolean algebra and Boolean equations that we can use to make this efficient from an engineering point of view. So in this lecture, we're going to show what those interesting tricks are, and we're going to put it all together in something called URP, the Unate Recursive Paradigm, which is an incredible, famous, powerful set of methods for doing interesting things on complicated Boolean objects. So we think we have a recursive strategy that'll do it. If we can't calculate whether a function is a tautology just by looking at its positional cube notation list, we should select a variable, split it into positive and negative cofactors. These are simpler objects. They have smaller data structures, we hope, and we should answer the question recursively. Only if they are both one tautology can the original function be one. And so this brings up a bunch of mechanical algorithm questions like what are the selection rules, like how should I pick the x? What are the termination rules? How do I know when I can actually stop and not recurse? And just, mechanically, how do I do all this stuff? Let's start with the mechanics because they're actually pretty easy. Now, I'll admit that this is a bit of a complex looking slide, but what I will just say is that this is just a recipe. This is just all the mechanics written down on one slide. How do you do the cofactors? How do you actually take the positional cube notation list and take a variable and either cofactor it by setting the variable equal to 1 or setting the variable equal to 0? This is what you do. All you do is you look at every cube in the list. If you're attempting to set the x to be a 1 to compute the positive cofactor, you look. If the slot for x has a 1, 0, well, that's an x bar. You make the cube go away. You remove it. If the slot has a 0, 1, well, that's actually got an x. When you set x to 1, you set it to a don't care because that variable also went away. And if the cube didn't have an x in it in the first place, well, you just leave it alone. You don't do anything to it. And the rules sort of flip. If you are attempting to compute the x equals 0 cofactor, if there's a 0, 1 in that slot, well, you should just remove the cube because there's an x there. If there's a 1, 0 there, well, you should just put a don't care there. And if there's a 1, 1 there, well, there's no x there in the first place. You don't have to do anything. It makes a lot more sense to just go look at an example. So here's a cube ABD, and here's a cube BC bar. What if you want to do f of a? And so we're gonna set the value of a to be a 1. Well, in this particular case, if you set the value of a to be a 1, well, in this cube that becomes a don't care because the a goes away and everything else in the cube stays the same. Right, so this is just a BD cube now. And similarly, if you set a to 1 in this cube, well, nothing happens. And the reason that nothing happens is that there wasn't an a here in the first place, and so there wasn't any work to do. Well, what if you take c and set it to be value equal to 1? Right, well, in the ABD cube, nothing happens because there's no c's. So 0, 1, 1, 1, 1, 1, sorry, 0, 1, 0, 1, 1, 1, 0, 1. Right, nothing happens, it's still the same. On the other hand, in the BC cube, right, because there's a C bar in the slot, this cube just goes away. Right, and that's one of the ways how, when you set the value of a variable to a constant to make a Shannon cofactor, the data structure representation of the cube list gets smaller. Some of the cubes vanish. Right, they just go away. You don't have to worry about them anymore. So that's a good thing. What about the selection and termination rules? How do you know which variable to pick, and how do you know when you can just look at the list of PCN cubes and calculate whether it's a 1 or not? Well, there's another really cool trick. There's a class of Boolean functions you've probably not been exposed to. They're called unate. And a function is a unate if in a sum of products representation, it has each literal, so that's just the appearance of a variable, in exactly one polarity. Either they're all true or all complemented. So this particular function, AB plus A C bar D plus C bar D E bar, is unate. And the reason it's unate is that you only see each variable in true form. So you see A's, but you don't see any A bars. And you see B's, but you don't see any B bars. And you see C bars, but you don't see any C's. And you see D's, but no D bars. And you see E bars, but no E's. It doesn't matter what polarity. They don't all have to be positive. They don't all have to be negative. They just have to be one polarity, right? So this other function here that I'm showing here is not unate. And it's not unate because, among other things, I see x's and I also see x bars. However, it's possible for it to say that it is unate in a specific variable, so it's actually unate in variable y. And the reason for that is you only see y's but no y bars. And the terminology is that we say that the function is positive unate in a variable, right? If changing the value of the variable from 0 to 1 keeps the function constant or makes it increase, go up, 0 to 1. And it's negative unate if changing that value of x from 0 to 1 keeps the function constant or it makes the value of the function go down from 1 to 0. And a function that's not unate is called binate. And it's sort of an analogy that I think is helpful here. This particular function, y equals f of x, is monotone non-decreasing. So if I take a value of x1 here and I increase it, right, to a value of x2 here, what we can see in the function is that either it's flat or it goes up. That's what monotone non-decreasing means. It means it doesn't get smaller. Unateness is exactly this same kind of a concept, but for a Boolean expression, for a Boolean function expressed in a sum of products form. Right? So suppose that we have a positive unate variable x, then if this variable gets bigger, goes from 0 to 1, just like the graph above, then what happens on the output is that either f goes from being a 0 to a 0, or it goes from being, a 1 to a 1, which is to say it stays flat, right? Or it goes from a 0 to a 1, which is to say it increases. Right? So this is kind of like flat or up in the monotone non-decreasing function, but in the Boolean universe. Now, why we care about this is really sort of surprising. First, let's just convince ourselves that it's not hard to check. Right? So suppose you have a cube list for f. A cube list is unate if each variable in each cube only appears in one polarity, not both. We don't care what polarity, just one polarity. So this function that I'm showing on the top is unate, and the function that I'm showing on the bottom is not. And it's much easier to sort of do visually if you put them vertically and just ignore the don't care. So I'm just going to cross out all the don't cares here. Okay, and then what you can see is, oh look, A appears in one polarity, it just appears in the 0, 1 polarity. B appears in one polarity, it appears in the 1, 0 polarity. C appears in one polarity, it appears in the 0, 1 polarity. You can see that it's very easy to check this mechanically. You just walk down all the cubes, and for each cube you look in the slot and you say, is this the same as all the other cubes or not? Yes or no? And in this one you can see, right, if I cross out the don't cares, you can see that this one is immediately the problem. B appears in both B and B bar. So it's not unate in this variable, not unate. Now, why do we care about this? Because there's a beautiful result. It's easy to check a unate cube list for tautology. A unate cube list is a tautology if and only if it contains the all don't care cube. And that's literally a cube where every single slot is a 1, 1. Now let's just think for a minute, what is that as a product term? So here is clearly a positional cube notation cube for the product ABC. And if I take the C variable and I make it a don't care, this is clearly the positional cube notation for AB. And then if I take another one and I make it a don't care, this is clearly the positional cube notation for A. But if I do it again, what do I get? And the answer is, that's how you represent a 1 in this business. You just put the all don't cares. That's like circling the whole Carnot map, right? And this result actually makes sense. The only way that you can make a 1 with product terms where all the literals are in exactly one polarity is if every one in the Carnot map is on. There's no other way, because if you actually try to circle terms in the Carnot map and have every single product term appear with its literals in exactly one polarity, there will always be one square in the Carnot map that you can't find. Try it. It's a good little exercise. Try it. Convince yourself. So we can look for tautology directly if we have a unate cube list. That's a wonderful thing. So I get two quick rules here. The first rule says the cube list is a 1. It's a tautology if it has the all don't care cubes at this leaf. Right? So that's kind of simple. Right? If it's got all 1s in it, doesn't matter what's going on. It's like saying, oh, look, this is stuff plus 1 plus stuff. Right? So this is easy, and in fact, I'd even say this is trivial. Right? This is not rocket science here. 1 plus a bunch of stuff is 1. Rule 2 is the interesting one. Rule 2 is the flip of that. It's not 1 if the cube list is unate and the all don't care cube is missing. Right? So you go check and you see if the cube list is unate, and then you know that if the all don't cares cube is not there, it cannot be unate. It cannot be tautology, and you can quit right now. You don't have to recurse. You can just stop. So again, I'm crossing out everything. Oh, look, all of the A's are in one polarity, all of the B's are in one polarity, all of the C's are in one polarity, but there's no all don't cares cube here. So it's unate, but the all don't cares cube is here. It's not a tautology. It cannot be a tautology. You can return a 0. Right? So this one returns yes for a tautology, and this one returns no. So these rules are important because it means that you don't always have to go down to one cube at the bottom before you can calculate stuff. You can calculate that you can stop and return an answer with big, very complicated lists of cubes. And you can have some more rules if you like. This is a more mechanical kind of a rule. What if you have a single cube that appears in both polarities that just has one variable in it, right? So in this case, we have one cube over here, which is just, let's say, x, and we have another cube over here, which is just, say, x bar. Oh, look, that's x plus x bar. That's a 1. Yes, you can return a 1. And you get the idea. You can have a lot more rules if you like, but it's generally the case that you don't want too many rules because there's a computational cost in checking them. So there's some balance between the complexity of the rules for your termination conditions and just sort of recursing a little bit further. Now, I got one more mechanical step that we need to figure out, and it's that, I can't use the nice termination rules unless I have a unate cube list. So when I pick variables to split on, maybe I should try to pick the splitting variables to force the cofactors to be unate. So the big idea is to pick the most not unate variable as the variable to split on, the variable to cofactor on. So you try to pick the most binate variable. And this is a heuristic, right? No guarantees. Heuristic, exclamation point, exclamation point. This works pretty good, but I can't guarantee it. So what you do, just as I said before, go in and figure out for every single variable, which ones are unate and which ones are not. Okay, so x is binate and w is binate, right? They are not unate, so those are the variables we should focus on, x and w. But they are both present in 4 cubes. So your first heuristic, sort of your first rule, is pick the binate variable that appears in the most product terms. And the reason you basically want to do that is that you'll simplify more cubes. There's the possibility that more cubes will vanish. Right? So you want to pick the most binate variable that appears in the most cubes. But what if there's a tie? And that's true here. Both x and w are binate, and they both appear in 4 cubes. Now what do? Well, you calculate how many cubes they appear in with true form and how many cubes they appear in with complement form. So that's how many places do you see x bars versus how many places do you see x's. And you just calculate the absolute value of the difference, and you pick the smallest value. And the reason you do that is that probably you're going to balance the complexity of the positive cofactor tree and the negative cofactor tree. They're both going to have basically the same amount of work, and a balance is usually good in this. And again, no guarantees, it's just another heuristic. So in this case, you would pick X because it appears in 4 cubes, but it's the difference between its true and complement count is 0. It appears in 2 true cubes and 2 complement cubes. That's a 0, that's the smallest number, and that's the what you pick. And so this is the algorithm. It's not all that much to it. It has a bunch of rules for, for termination, right? So the first thing you do in any recursive algorithm is say, hey, can I compute the answer and stop, or do I actually have to do some work? And if the answer is that you cannot compute the answer and stop, right, then you have the selection problem where you figure out the most not unate variable. And then you have the recursion where you call tautology on the positive cofactor and the negative cofactor. And the really cool thing about this is that that's just code, right? Each of these things returns a Boolean 1-bit value, true, false. You just AND them together in standard code fashion, and that's what you return. It's a beautiful little algorithm. Here's just a little example, showing what happens. So suppose I've just got this positional cube notation list at a node of the tree, and I'm trying to figure out what to do. And so the first thing I do is I look at it and I say, wow, that's too complicated. I can't compute the right answer. And it turns out that all of the variables are binate, and A affects the most implicants. It's in the most product terms, so we'll split on A. Right? So when we go down this side of the recursion, we're setting A equals 1, and when we go down this side of the recursion, we're setting A equals 0. And so when we set A equal to 1, what happens? Well, we're going to pass in a cube that looks like 1, 1, 0, 1, 1, 1, and so that's just the B cube, right? Because the A goes away, and then we're going to pass down a cube that looks like 1, 1, 1, 1, 0, 1. That's a C cube because the A went away in the second cube. And then we're also going to pass down a cube that looks like 1, 1, 1, 0, 1, 0. That's a B bar C cube because the A went away. But when we go down this side, the A bar cube, right, this cube, right, that one just went away because when you have a cube that just has an A bar in it, when you set A to 1, that cube goes away. That cube vanishes, right? That's a 0. So only 3 cubes go down there, and then it turns out you're going to have to recurse some more because you can't actually tell anything about the value from this. There are no rules to apply. Whereas on the other side, if you set A to 0, the first cube goes away and you don't pass it. It's a 0. The second cube goes away and you don't pass it. The third cube goes away and you don't pass it. And again, I'm emphasizing the whole reason for sort of careful selection of the splitting variable is to try to kill as many cubes as you can. And then the fourth cube, A bar, when you set A to 0, hey, there's the all don't cares cube. So this thing has a 1 in it, and so it's a tautology. So this one can just immediately send back a yes. And I'm just finishing it out here so you can see what happens. On the left-hand side, when you go down and recurse and set B equals 1, right, on the left-hand side, you get an all don't cares cube, so that's a 1. And on this one, you get the C plus C bar rule 3 that we gave, and that one's a yes. And so this function is actually, yes, this is a tautology. Every single one of these things computes a yes, and this is the computation tree that is traced out. It has tautologies at all the leaves, and so this is in fact a tautology, and we're done. This computational philosophy, if you will, is very famous and very general, and it has a name. And so this is called the unate recursive paradigm. It's a paradigm because it's actually a big and impressive sort of a family of algorithms. It's recursive because we use the Shannon cofactor as the critical step to take a complicated problem and make it simpler solvable. That's our divide and conquer. And we use unate because it's just this really clever trick that makes it possible to calculate complicated things, tautology on complicated representations without a lot of work. And so it's usually called URP. Please don't call it URP. Nobody calls it URP, URP, Unate Recursive Paradigm. So here we are at the end of our introductory lecture set on computational Boolean algebra. What have I told you? Cofactors, Shannon cofactors are really important. And functions of cofactors are really important. The Boolean difference, universal and existential quantification, network repair. There's some amazing things you can do once you understand cofactors. And representations, data structures for Boolean functions, those are really critical. In order for you to actually compute stuff, you got to have a data representation. And we showed you a very simple one, cube list positional cube notation. And with the cofactor ideas, we were able to compute something really hard, tautology using the unate recursive paradigm. So look, truth tables, Carnot maps, equations, it's just not easy to manipulate those things with software. The positional cube notation, that's one good way of doing it, but it's not honestly the way most people do it. The next week's lectures are lots of stuff about how people actually do the representational problems for computational Boolean algebra.